Hello friends, in the last few sessions we have covered the basics of link layer and discussed in brief some of the basic services provided by the link layer. We have also discussed the broadcast networks and multiple access protocol. Now in this and next part we will explore switched LAN and link layer addressing. So far in our previous sessions we have covered broadcast networks and multiple access protocols. Now we will discuss about switched local networks and how switches operates at link layer and how link layer addresses are used to forward the link layer frames through the network of switches. We will first start with switched LAN and link layer addressing. Hosts and routers have link layer addresses. Now you might find this surprising as we already know that hosts and routers have network layer addresses as well. One question may be cropping up in your mind that why in the world do we need to have addresses at both the network layer as well as link layers? In addition to describing the syntax and functions of the link layer addresses, in this section we will try to shed some light on why the two layers of the addresses are useful and in fact indispensable. We will also cover the address resolution protocol, that is ARP, which provides a mechanism to translate the IP addresses to link layer addresses, that is MAC addresses. In truth, it is not hosts and the routers that have link layer addresses, but rather their adapters, that is the hardware network interfaces that have link layer addresses. A host or a router with multiple network interfaces will thus have multiple link layer addresses associated with it, just as it would have also multiple IP addresses associated. It is important to note, however, that link layer switch do not have link layer addresses associated with their interfaces that connect to hosts and routers. This is because the job of link layer switch is to carry datagrams between hosts and router. A switch does this job transparently, that is, without the host or routers having to explicitly address the frame to the intervening switches. A link layer addresses is variously called as LAN addresses or a physical addresses or more popularly termed as MAC addresses. For most LANs, including the Ethernet and 802.11 wireless LANs, the MAC address is 6 byte long. Giving 2 raised to 48 possible MAC addresses. These 6 byte addresses are typically expressed in hexadecimal notation, with each byte of the address expressed as a pair of hexadecimal numbers. Although MAC addresses were designed to be permanent, it is now possible to change an adapter's MAC address via software too. Here the MAC address is 6 byte. Hence, there are 48 bits, which gives rise to 2 raised to 48 different MAC addresses. which can be used to address all the hardware as well as adapters used in the network. A host or a router with multiple network interfaces will thus have multiple link layer addresses associated with them, just as it would have multiple IP addresses associated. But the link layer switches do not have link layer addresses associated with their interfaces that connect to hosts and routers. It is neither the host nor the routers that have link layer addresses, but rather their adapters. These are the adapters with whom the LAN address or the MAC address is associated. It is neither the host nor the routers, but it is an adapter which is having the MAC address. This MAC address is 6 byte long, which gives us a total address space of 2 raised to 48 different combinations. One interesting property about the MAC addresses is that no two adapter can have the same addresses. This might seem surprising given the fact that adapters are manufactured by different countries, located at different places, maybe in different countries. Then how a company manufacturing an adapter in one country does ensure that it is using different addresses from a company manufacturing adapter in other country? Answer to this question is that IEEE manages the MAC address space. In particular, when a company wants to manufacture adapters, it purchases a chunk of address space for nominal fees. IEEE does allot chunk of 2 raised to 24 addresses by fixing the first 24 bit of the 6 byte MAC address and letting the company creates unique combination of last 24 bits for each adapter. An adapter's MAC address has a flat structure as opposite to the hierarchical structure and does not change no matter where the adapter goes. For example, a laptop with an Ethernet interface always has the same MAC address no matter where the computer goes. Or a smartphone with an 802.11 interface always has the same MAC address no matter where that smartphone goes. Recall that in contrast to the IP addresses, which is having the hierarchical structure, that is a network part and the host part, which we have seen in our earlier sessions, a host IP address need to be changed when host moves, that it changes the network to which it is attached. An adapter's MAC address is an analogous to a person's social security number, which also has a flat addressing structure, which does not changes no matter where the person goes. The person's social security number remains same irrespective of the location of that person. An IP address is analogous to person's postal address, which is an hierarchical in nature and must be changed whenever a person moves from one location to other. Just as a person may find it useful to have both postal addresses as well as the social security number, it is useful for the host and the router interfaces to have both network layer addresses and the MAC address. When an adapter wants to send a frame to some destination adapter, the sending adapter inserts the destination adapter's MAC address into the frame and then send frame to the LAN. A switch may occasionally broadcast an incoming frame onto all of its interfaces. As a result, an adapter may receive a frame that is not addressed to it. Thus, when an adapter receives a frame, it will check to see whether the destination MAC address in the frame matches with its own MAC address. If there is a match, adapter extracts the enclosed datagram and passes the datagram up to the protocol stack, up in the protocol stack. If there is not a match, adapter simply discard the frame without passing the network layer datagram up. Thus, the destination only will be interpreted when the frame is received. However, sometimes a sending adapter does want all other adapters on the LAN to receive and process the frame it is about to send. In this case, the sending adapter inserts a special MAC address, which is called as a MAC broadcast address, into the destination frame address field of the frame. For LAN that uses 6-byte addresses such as Ethernet and 802.11, the broadcast addresses is a string of all 48 consecutive ones, that is FF, 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 all 1. This is an hexadecimal notation. This is a typical MAC broadcast address, which is used when sending adapters wants to send frames to all the adapters in the LAN. There are both network layer addresses, for example, internet IP addresses, and link layer addresses, that is MAC addresses. Hence, there is a need to have translation between them, which in case of internet is done by address resolution protocol, that is ARP. To understand the need for protocols such as ARP, let us consider a network as illustrated here. In this simple example, here each host and a router has a single IP address and a single MAC address. As usual, IP addresses are shown in dot decimal notation and MAC addresses are shown in hexadecimal notation. Here, for the sake of better understanding, we will assume that the switch broadcasts all frames. That is, whenever a switch receives a frame on one interface, it forwards the frame to all of its other interfaces. This is a typical switch which broadcasts all the frames. Now suppose that the host with an IP address 222.222.222.220 wants to send an IP datagram to a host having an IP address 222.222.222.222. That is, this typical host wants to send an IP datagram to this particular host. That is, both the source as well as the destinations are in the same subnet. To send a datagram, the source must give its adapter not only the IP datagram but also the MAC address for the destination 222.222.222.222. Along with this IP address, it must also give the MAC address. Sending adapter will then construct a link layer frame consisting of destination's MAC address and send the frame into the LAN. When this particular host is sending a datagram, it needs to insert the MAC address of the destination. Here the important question arises are, how does the sending host determine the MAC address for the destination host with IP addresses? Here this particular sending source host knowing the IP address of the destination host. But the question arises, how this source knows the MAC address of the destination? Here, in this case, the sending host, that is 222.222.222.220, provides its ARP module the IP address of the destination, that is 222.222.222.222, and the ARP module returns the corresponding MAC address 49-BD-BD2-C7-56-28. This is how ARP, that is Address Resolution Protocol, resolves the IP address to a MAC address, and in many ways it is analogous to the DNS, which resolves the host name to IP address, which we have already discussed. However, one important difference between the two resolvers is that DNS resolves host name for host anywhere in the internet, whereas ARP resolves IP addresses only for the host and router interface on the same subnet. Each host and router has an ARP table in its memory, which contains the mapping of IP addresses to MAC addresses. This is a typical structure of an ARP table, which is available in the memory of individual hosts. The ARP table also contains time to live value, which indicates when each mapping will be deleted from the table. This is a typical example of an ARP table of these hosts 222.222.222.220. It consists of an IP addresses of other hosts along with their corresponding MAC addresses. And one more field, that is TTL, time to live, which indicates when this each mapping will be deleted from the table. Note that table does not necessarily contain an entry for every host and routers on the subnet. Some may have never been entered in the table and others may have expired. If for sake of understanding, we are considering that this particular host is having an entry for the remaining two hosts, which is belong to the same subnet. But it may be the case that subnet may consist of number of hosts and the entries in the particular ARP table does not include the corresponding entry for all the hosts in the same subnet also. Typical expiration time for an entry in an ARP table is 20 minutes from when an entry is placed in the ARP table. By default, at the max, the threshold value of TTL is 20 minutes. After each 20 minutes, the particular entry will be either replaced or deleted. Now suppose that the host 222.222.222.220 wants to send an IP address to another host or router on that subnet. Sending host needs to obtain an IP address of that particular destination given the IP address. Here, the IP address of the destination is known. From that destination address, one can obtain the corresponding MAC address. This task is easier if the sender's ARP table has an entry for the destination node. Here, this ARP table is used to have mapping between the IP addresses and corresponding MAC addresses. As we have discussed, we know that it is not essential that ARP table must consist of entry for all the hosts in the same subnet. What if the ARP table does not currently have an entry for the destination? In particular, suppose the host having IP address 222.222.222.220 wants to send a datagram to an host having IP address 222.222.222.222. In this case, the sender uses ARP protocol to resolve the address. First, the sender constructs a special packet called as an ARP packet. An ARP packet has several fields, including the sending and receiving IP addresses and MAC addresses. Both ARP query and response packets have the same format. The purpose of ARP query packet is to query all other hosts and routers on the subnet to determine the MAC address corresponding to the IP addresses that is being resolved. Returning to our example, that is source host passes an ARP query packet to the adapter along with an indication that adapter should send packet to MAC address broadcast address, namely ff-ff-ff-ff-ff. As we know, these all ones is a broadcast MAC address. The adapter encapsulates the ARP packet in a link layer frame, uses the broadcast address for the frame's destination address, and transmit the frame into the subnet. Just recall our social security number and postal address analogy. An ARP query is equivalent to a person shouting out in the crowded room of a cubicle of in some company, like, what is the social security number of the person whose postal address is XYZ cubicle room number ABC, certain company at certain place in certain country. For example, cubicle number 13, room number 112, TCS, Pune, India. This is a postal address. What is the corresponding social security number? The frame containing the ARP query is received by all other adapters on the subnet. And because of the broadcast address, each adapter passes the ARP packet within the frame up to its ARP module. Each of these ARP modules check to see if its IP address matches the destination IP address in the ARP packet. The one with match send back to the query host a response ARP packet with a desired mapping, that is desired MAC address. The querying host, in our case that is 222.222.222.220, can then update its own ARP table and sends its IP datagram encapsulated in link layer frame whose destination MAC address is that of the host or router responding to our earlier query. There are a couple of interesting things to note about the ARP protocol. First, the query ARP message is sent within a broadcast frame. whereas the response ARP message is sent within the standard frame. Second, the ARP is a plug and play. That is, an ARP table gets built automatically. It does not have to be configured by system administrator. And if host becomes disconnected from the subnet, its entry is eventually deleted from the other ARP table in the subnet. ARP is simple plug and play. An ARP packet is encapsulated within link layer frame and thus lies architecturally above the link layer. However, an ARP packet has field containing link layer addresses and thus is arguably a link layer protocol. But it also contains network layer addresses and thus is also arguably a network layer protocol. Here in this session, we have covered the basics of MAC address format and the significance of ARP table. We have also discussed the working of ARP protocol, specifically in moving the datagram within the same subnet. In the next session, we will discuss how datagram can be moved across different subnet. Stay tuned. Thank you.